Let's take a look at today's lesson. We're going to be looking at symmetry and transformations. Both of these topics you would have already, gone through like last year, maybe some previous to that. But we're going to get a little bit more in depth. So let's start with symmetry. All right, so we have axis of symmetry. That's a line that basically, this would be considered, this L would be an axis of symmetry. It's possible to pair the points of the graph in such a way that L is the perpendicular bisector of the segment joining the pair. So here's a pair that's a perpendicular bisector. Each side is equivalent. That's kind of a geometry thing, right? That takes you back a couple of years ago. So that's a geometry definition. A point of symmetry of a graph is possible. It's possible to pair the points in such a way that that point of symmetry is the midpoint of the segment joining each pair. So this is an example where 0 would be the point of symmetry, and we can see these segments that are drawn. This would be the midpoint of the pair of segments. So this is another pretty important thing. I don't have an example about the cubic functions, but I do. We need to talk about them, and it's important to know that every cubic function has a point of symmetry. Every single one of them. You'll have questions on the daily work and quizzes or tests or such. This is how you would find, it's a formula, that's how you would find the x value of the point of symmetry of a cubic. Just that little formula, x equals negative b over 3a. Once we had the x-coordinate of that point of symmetry, how would we find the y-coordinate? Just plug it in, right? Just plug it in. So that's if we have an equation. Let's say we don't have the equation. Let's say we have maybe the point of symmetry and a minimum or a maximum. And that's going to happen. So I'm just going to kind of walk through and show you what that means. So let's say we have a cubic. I'll just kind of draw an example. Let's say, okay, that's a terrible looking cubic, but let's just pretend that that's a good looking cubic. And what we would have would be, if we would connect the maximum and minimum points together and drew a line, this, where they meet right here in the middle, would be the point of symmetry. Okay, so how would we do that? How would we find the midpoint of a line segment? We would use the midpoint formula, right? Hopefully we remember that. If it's a cool formula, I like it. It makes sense. How would you find the midpoint of something? Well, you would take the x-coordinates of these two outer points and average them. Add them together, divide by 2. Remember that formula? The y-coordinates, you would take the y-coordinates of these two outside points, you would add them together, divided by 2, and that would give you the midpoint. So that is something, I'm reminding you about it because that's something that you'll need to be able to do given the given the point of symmetry of a cubic and say the maximum value, could you find the minimum value? And that answer would be yes. You would have to use the midpoint formula. Okay? I just don't have an example about that, but if I did an example of every single thing, we would be here like forever. So just kind of pointing that out to you, that is something that's going to be important for us to know. So let's get back to our symmetry. We have 4 symmetry tests, and I'm going to go through each one. So to test for symmetry in the x-axis, what we would do is we would replace the y with the negative y, and if we get the same thing we started with, then it has x-axis symmetry. This is an example of an equation that has x-axis symmetry. We can see the graph of it, see how it reflects over the x-axis. So we plugged in a negative y for the y. We got the same thing we started with. It does have x-axis symmetry. The next one is y-axis symmetry, which actually has another name. This is pretty important, an even function. So really, to be perfectly honest with you, the 2 most important symmetries for us are going to be the even and the odd functions. That we carry on with us to calculus, even and odd. I've even seen an AP question that talks about an even or an odd function. So that is something that we really need to stick with. So symmetry in the y-axis or an even function, we would replace x with negative x and get an equivalent equation. So this is an example of symmetry in the y-axis or an even function. Let's think back into the past, all right, into trig. We love trig. So remember the 6 trig functions? 2 of them were even. Do we remember which 2 were even? And this is a formula you need to know. Cosine, very nice. Cosine and secant were even. So that's something that we use in calculus, you know, to simplify things. So cosine and secant were even. The rest of them were odd. Okay, so that's the even-odd property. Excellent. All right, so that is for even functions. So the next test is symmetry in the line y equals x. That really, this is a graphical test to determine inverses. You know, if the inverses are, well, if we have 2 different functions, this is a graphical test to consider to determine symmetry, or excuse me, inverses. If you look at this, here's my line y equals x. This particular unusually shaped graph is symmetrical over that line, over the line y equals x. Then for an odd function, that's symmetry at the origin, we would, now there's 2 tests for odd functions. I'm going to be straightforward with it. There's 2 tests. This test really pretty much works with everything, although I think it's a little confusing. This test over here, this test for odd, we typically use for polynomials and different kinds of things like that, or rationals or radicals. So here, let's look at this test. What we do is we replace x with negative x and y with negative y, and if we get the same thing we started with, we are good. Okay, that's what we're doing here. We're replacing x with negative x and y with negative y, and basically that is the same thing we started with. Because I could divide the negative 1 off, right? Couldn't I divide both sides by negative 1 and it would go away. So I would just have y equals x cubed. The other odd test, I'm going to just go straight to it so we're all together. The other odd test is where we do f of negative x. If we plug a negative x in and we get exactly the opposite of what we started with, then that is a different test for odd. Okay? So those are different tests. If one doesn't work, you might try the other one. I'm just saying both of them are not in, well, this one I think is confusing but will work with everything. This one right here, replace x with negative x, y with negative y, and then, you know, simplify. It will work. This one I think is easier and more straightforward, and it works with most things. Most things. Okay? So since we're talking about even and odd properties, let's just continue on with that concept. So f is even if, this is the test right over there, if I do f of negative x and I get f of x, then it's even, and then we already talked about the odd test. We've already talked about what a graph looks like when it's even and what it looks like when it's odd. And I have another little blurb out here about our lovely cubic and points of symmetry for the cubic. I wrote that x equals negative b over 3a there again for us. Okay, just to highlight. So the other topic we're going to be looking at today is transformations. Okay, so here it's really, to be honest, this is just a review. We've been doing this for quite some time. We even did this with trig functions when we were graphing trig functions, remember all that transformation stuff? And so just, you know, if this means it's a right shift, a left shift, we know x is just kind of fussy. It does the opposite of what you want it to do, right? If it says minus c, then it's plus, you add c, and then if it says, you know, you go right. If it says plus c, then you go left. I mean, it's opposite of what you would think. Y is pretty straightforward. If it says plus, you know, whatever 3, you would go up 3. Minus 3, you'd go down 3. Then we have these multiplication and division transformations. These are the addition and subtraction ones. These are the multiplication and division ones. So if we, you know, this would be a reflection over the x-axis. This would be a reflection over the y-axis. This is a stretch, a vertical stretch, and a horizontal stretch. Okay, those are just a quick review on transformations. Okay, any general questions before we jump into the examples? All right, let's go to the next slide. Let's take a look at our examples for today. Okay, so the first one, we are going to graph that with symmetry, which means we need to run through all 4 symmetry tests to determine, you know, which symmetries we have, and then we will graph. Okay, so we're going to just go in the order that's on the other page. You know, we have x-axis symmetry. The x-axis symmetry, if you recall, I replaced the y with a negative y. So let's do that. And then I simplify. I came out with the exact same thing that I started with, so check, it does have x-axis symmetry. The next test was y-axis symmetry, an even function. For that test, we would replace the x with a negative x and simplify it. And check, it has y-axis symmetry also. The next test was to determine if it's symmetrical over the line y equals x. So I basically take the x and the y and I switch their places. Everywhere there's an x, I put a y. Where there's a y, I put an x. So I'm just going to switch their places. Is that the same thing that I started with? Yeah. So it has that symmetry also. Wow, this one's really, you know, has a lot of symmetry. The last one is the origin symmetry, which is also odd. We're going to do the test where we replace x with negative x and y with negative y. And then simplify. And it has origin symmetry also. Whew, this little guy has got all 4 types of symmetry. So I'm really not going to have to plot that many points because I'm just going to pick a point and then I'm going to do all that symmetry thing to it. So I started with what happens when x is 0, then y is 2. So I plotted that point 0, 2. And then I'm going to do all the symmetry. So let's do the x-axis symmetry. If it has x-axis symmetry, that means it reflects over the x-axis, so I know there's a point right here. If it has y-axis symmetry, there's really nowhere to move, right? It's on the y-axis, so that's not helpful. The line y equals x, let's go ahead and draw that line so we can reflect over it. So that line y equals x, just going to kind of put a dotted one right there. All right, so then that means this point would reflect over this line, right? So if I have a point here, I'm going to have one here. And if I have a point here, I'm going to have one here. Okay, so we've taken care of all the symmetry for that point. Let's just pick, we just need one other point. Let's choose 1. When x is 1, y is 1. So here. Okay, so let's do all of our symmetries. Let's do our x-axis symmetry, so we're going to reflect over the x-axis. Our y-axis symmetry, so we'll reflect over the y-axis. And really we have enough points to be able to draw this graph. It is a strange little looking graph. I kind of like it. Kind of looks like a diamond. There's our graph. And we graphed it with symmetry. Okay? So that's just practice going through the 4 symmetry tests and using it to graph. Okay, questions on that? Okay, let's look at number 2. The greatest integer function. Students just love the greatest integer function. I think it's a confusing function, especially its name. Its name troubles me. It says greatest integer, but we all know that what comes out of that is going to be the integer lower. Like if I put a 1/2 in the greatest integer function, 0 is going to come out, not 1. Right? Do we remember that? It's kind of like, you can kind of think about it as round down to the nearest integer. I guess you could think about it that way. Although it's called the greatest integer function. It's like, what? You're calling it the greatest integer function? Does it just mean that's great? It's fantastic? It's a great integer function? So I don't know. I don't really know what that means, but it's just a little troubling. So what I like to do, I don't do transformations with greatest integer function. I think that's really confusing. I just plot points. So we're going to just plot points. If you want to do transformations with it, you certainly are welcome to. You do not have to plot points if you don't want to, but that's what I do. I'm just going to plot points, and I start with integer points. I want to see where the integers are, and then I'll worry about fractions. Okay, so I would start with 0. You know, and 2 times 0 is 0. Greatest integer of 0 is 0. 0 plus 1 is 1, so I know that's a point. Then I would just put in a 1. 2 times 1 is 2. Greatest integer of 2 is 2. 2 plus 1 is 3. So I'd go here, plot that. I need another one just to kind of determine the pattern of this. So I'll do a 2. 2 times 2 is 4. 4 plus 1 is 5. Okay, so I have that pattern down, and I would just fill the rest of the graph with that. I know those are all legitimate points, so I would fill them in. I can't draw the little bars with the open circles yet because I don't know what's going on. I'm going to pick some more values, like let's see what happens in between here. Let's see what happens at a half. Well, 2 times a half is 1, and the greatest integer of 1 is 1. 1 plus 1 is 2, so at 1/2 I'm at 2. So it looks like at all of the half points I'm up. So if we wanted to test that again, that's like 1.5. If we put a 1.5 or 3 halves in here, 3 halves times 2 is 3. 3 plus 1 is 4. So at 3 halves I'm at 4. Okay, do we see that pattern? So I can just fill out those integer patterns. So I'm going to fill those out. So that puts us right here and there. Okay, well, goodness gracious, we haven't got to fractions yet. Let's keep going. So let's see what happens between, let's see, what did I do? I did, I think 3/4. Yeah, let's see at 3/4. So in here, what's going to happen at 3/4? So I'm going to actually have to do some fraction work now. So I would have 2 times 3/4. So 2 times 3/4 is what, 3 halves? So the greatest integer of 3 halves, we go to the one underneath it, right? So it would be 1. So 1 plus 1 is 2. So for 3/4, we're at 2. So let's see what that does to us. So 3/4, we're at 2. Okay, so now I know and can draw my little, they're little bitty tiny bars, right? Like a little half space bars. So now I can complete that graph. And when you are given a graph, I need you to complete the whole thing, you know, fill the whole thing in. So let's do that. And I'll try to give a little bit bigger spaces for us because that was a little bit hard to do with those little tiny things. So there is our greatest integer function. We have a good review of that. We okay with that? Okay. All right, let's go to transformations. So you can do transformations. You can transform that graph in your head if you want to. I'm fine with that. I don't do it that way. I plot points. That's what I do. But you can do it the other way if you want. Doesn't matter. So I'm going to plot points. I'm going to pick out like the corners and some important points, and I'm going to simply plot them. Okay, so here's my original. So I go what, -3, 0, -2, 1, 0, 0, 1, -2, 2, 0, and 1, 2, 3, 2. Okay, so these are the parent points. You might want to like highlight them. I don't know, put like a little asterisk there, because these are the ones that you would go back to every time, not the transformed points. These are like that's the parent points. We're going to go back to that for all the transformations that we're going to have to do. In this case, I just did 2 of them. We just did 2 of them. So let's look at the first one. I tried to do the 2 that are least common, that cause students the most trouble. And this one can cause students some trouble, and this one especially. This one I think is the hardest one. So let's look at this one. On this one, what they're telling us to do is, if you recall, what happens to the x is always opposite. It's being multiplied by -1, so we would divide all the x's by -1, which it's a -1 and it's the same thing, right? But if it were 2, that would make a difference. So we need to remember x is opposite. So I'm going to work on the parent points, and I only have one x transformation. If I had more than one x transformation, what's possible? then you would do the multiplication addition ones first, excuse me, the multiplication division ones first, and then the addition and subtraction ones, if you had more than one to do. And this should be review. We should have heard that before. It should be review. So we're going to take all the x's and we're going to alter their signs. So instead of a -3, it's going to be a 3. Instead of a -2, it's a 2. 0 has no sign. Poor little 0. 1 is -1, 2 is -2, 3 is -3. Okay, so we've done this transformation right here. Now let's work on the y transformation. The y transformation is a +1. So I'm going to take all the y values and add 1 to them. 0 plus 1 is 1. 1 plus 1 is 2. 0 plus 1 is 1. -2 plus 1 is -1. 0 plus 1 is 1. And 2 plus 1 is 3. Okay, so now I just plot the points and I have my graph. When I do it this way, I make fewer mistakes. Certainly you don't have to. You can just transform it in your head. But I make fewer mistakes when I transform points. So we'll go 3, 1, 2, 2, 0, 1, -1, -1, -2, 1, and -3, 3. So let's draw that. So that's my graph, and let's just think about and talk about the transformations. So this transformation is a reflect over what? Reflect over the y-axis transformation, right? You can see that this was reflected over the y-axis, and this transformation is shifting everything up 1, which it is. So by transforming points, I'm doing the transformations without even thinking about them, without even worrying about knowing how that works. Okay? I mean, it's important to know how it works, but it's really nice to have numbers to work with rather than just, oh yeah, just flip it and move it up. Okay, well, what does that look like? So that's just an option for us. This next one, I think, really is the most difficult one of all the transformations. The one where x is absolute valued, because it's so really weird. You know, when the y is absolute valued, this one, I think we all have that one down, right? That just means that I can't have any negative y's and it would flip up. And that's all this transformation means. That's not, I think that's a pretty easy transformation. This one, though, is very confusing. I'm going to talk about it in 2 different ways. So hopefully one of the ways that I talked to you about it will stick. So graphically, let's talk about it graphically. If I just think about it graphically, what I would do is I would take the left side of my original figure and I would throw it away. It's gone. And it's actually kind of sad. It's gone. And then I would take the right side of my figure and reflect it over. Graphically, that's what happens. This left side disappears, the right side is reflected, and I have my graph. And that's like so weird and sketchy. Why would you do that? Why would you just throw away that whole side and then reflect it? So let's look at it analytically. What does it mean? Okay, so let's do points. Now, just because the x is absolute valued, does that prevent me from putting any x in there? Can't I put any x I want to in there? Can I put a negative x in there? Yeah, right? I can put any x I want to in there. So all of my x values, we'll go back to the original. I made the mistake earlier of going to this one, and I see that on tests and quizzes all the time. So let's do something. Let's kind of, come on. Let's just put like a little cross through it so I'm not tempted to go back to that one. We need to refer to this one, the parent one, every time. All right, so let's go back to the parent one. So I can keep all those regular x's. Those are fine. So we're going to put those in there. So I get -3, -2, 0, 1, 2, and 3. So let's talk about analytically what happens. What happens when I put in a +1 in here? Does it change anything? It's still a 1. So my positive points, in other words, the right side, my positive points keep their same y values. So I'm going to go over here, my positive and poor little 0 that has no sign, they keep their same values. So I'm just going to copy their same y values. So I'm just going to copy those down. 1 is a -2, and 2 is a 0, and 3 is a 2. They keep the same values. But the negative x's are the ones that are messed up, Because what happens when I put a negative x in here? Doesn't it turn into, or no, let's just talk a specific number. What happens when I put a negative 3 in here? Doesn't it turn into a positive 3? Right? And don't we already have a y value for a positive 3? Yeah, I have to use that y value. See, that's analytically, that's what's happening. I'm putting in the negative 3, you know, it becomes a positive 3. Well, what output did the positive 3 have? Well, the output the positive 3 had was a 2, so that has to be a 2. So I put in a negative 2, it becomes a positive 2. What output did the positive 2 have? It has 0 as the output or the y value, so it has to be that. Okay? Now, because this is a weird graph, it's not my original graph, I may not have a complete picture over here on the left when I plot these points. So let's plot the points and see what happens. Again, I may not have a complete picture because I don't have all integers on here, do I? I'm missing like, what, -1? I don't have -1, so there may be some issues at -1 that we're going to have to work through. So let's plot these points. So I have -3, 2, then I have -2, 0, 0, 0, 1, -2, 2, 0, and 3, 3, 2. Okay, so I do. See, I have a missing point at -1. And that's because it wasn't in my original points. Because I didn't need it in the original graph, right? Can we tell what -1 is going to be? I mean, we should know that that right side is reflected, but let's say we don't. Let's go back to our original graph and see what happens at 1. So at 1, we were at -2. So where do you think we're going to be at -1? -2, right? Because the poor little negative has been ripped off of it and it has to take the y value of the positive one. So I'm going to be here at -2. And so here's my graph. So I talked about it both graphically and analytically. I hope that that helps. By far, I think that is the most challenging transformation. I think the other ones you guys have down. I mean, you could probably do those with your eyes closed. But this one is really hard. Are we okay with this one? Okay. So let's do our last one is to determine whether the function is even, odd, or neither. So we're going to do that test where we find f of -x. So that would be -x squared plus a -x. So I simplify that, and I get x squared minus x. Do I have the exact same thing that I started with? No. Do I have the exact opposite from what I started with? No. So this is neither. To be even or odd, I need either the exact same thing I started with or the exact opposite of what I started with using this test, this f of -x test. So this is neither. It doesn't have either one of those symmetries. Okay, this one with the -2, that troubles me just a little bit. I'm going to turn it into a positive exponent. So I'm going to make this 1 over x squared. Okay, so now let's do our f of -x. So f of -x is going to be 1 over -x squared, or 1 over x squared. Okay, do I have the exact same thing that I started with? Yes, so which symmetry does this mean? Even. This is even. So this is even symmetry. Okay? How are we? Is everybody okay?